Alrighty, ladies and gentlemen, I'd like to do a couple of videos here, a short discussion about thermodynamics, and I'm gonna get away from what's in the text and kind of concentrate on what I think is the most important stuff. Okay, um, so thermodynamics is basically the study of how heat moves around and how we can get it to do things for us. So the basic story about thermodynamics, well, there's basically four laws: the zeroth, first, second, and third law of thermodynamics, and they tell the story of the attempts to use heat to do work. In the old days, if you wanted some work done, you wanted a hole to be dug, or you wanted some water to be pumped from a pond across your field so you could grow some stuff, you had to have manual labor yourself, or maybe some sort of farm animal doing that for you. But eventually, people realized that you could build a fire and burn some wood and get a high temperature, and then develop a device that took some of that heat flowing from the high temperature fire to actually do your work for you. And that's the story of thermodynamics. The downside is, in previous incarnations of conservation of energy, and that's what this really is, um, you could have all of the potential energy become the kinetic energy. But when the heat flow is involved, there's some gotcha moments, because as the heat flows, the temperature of the thing that is hot will decrease, and so you'll get less heat flow. So you can actually kill the golden goose, if you remember that story. So the zeroth law of thermodynamics, and this is just for fun here, zeroth law. And I don't even know if that's how you spell zeroth. Maybe there is an E in there. I don't know. The zeroth law of thermodynamics says that if object A is in thermal equilibrium with object B, their temperatures will be equal. And if object B is in thermal equilibrium with object C, then you can conclude that object A would be in thermal equilibrium with object C. This, I believe, is the transitive property of logic. I'm not sure about that. Maybe somebody could look that up for me. Um, and uh, and seems kind of silly, but this is works if object A is a thermometer. In other words, you can use a thermometer, place a thermometer in contact with object B until it becomes in thermal equilibrium, and then you can read the temperature. And then, of course, if object B is in thermal equilibrium with object C, you can conclude that they're going to be at the same temperature. Or you could consider object B to be the thermometer. You touch it to two different things and get readings. But this basically says that you can use a device called a thermometer, which comes to thermal equilibrium with various devices. If you remember the old-fashioned thermometer, the one that had the fluid in it, the ones we use in the classroom have a denatured alcohol. The ones you use for a fever often have a small amount of mercury. You have to put those in contact, or put them in the mouth of your child, and leave them there for a while so that they can come to thermal equilibrium. All right, the first law of thermodynamics. First law of thermodynamics says that the change in internal energy of a system is going to be equal to any heat you add to the system or any work done by the system. Okay, so let's graph these out. This is the internal energy of the system. That's the unknowable total amount of molecular jiggling going on with any system. This is the heat that you would add to the system. In other words, this is a positive number if you put heat in, and a negative number if you take heat out. And this is the work that system might do. Now, what do I mean by a system? Well, what if we had like a glass jar, and I don't know how to draw a glass jar, so we'll just draw something with a lid on it there. And inside this glass jar were a bunch of gas molecules. That's what would happen if you sealed up a glass jar. And that internal energy of all these jiggling molecules, well, if I set this out on the windowsill and the sun shines on it, why, heat is going to be added. Or if I make this gas in here do some work, like if I had a lid that was able to be moved up and down like a bellows or something, then I would lose internal energy because the gas would be pushing this lid up and down. So that's what I'm talking about when I say a system. We just say, hey, some sort of thing that we can use. Okay, so basically, how do you let's talk about the second law. Okay, the second law says that heat can only flow from high temp to low temp by itself. And I have to say by itself because there is a way to make heat flow from low temperature to high temperature. And that's what we're going to get to here. We're going to talk about heat engines, which are devices that use the flow of heat to do some work. But if you want heat to go away from some place where it's already cold, like the inside of your refrigerator in your kitchen, you can do it. You just have to put some work into it, okay? And the third law of thermodynamics says that the overall entropy of the universe must increase for any process. Nothing can happen unless the overall entropy of the universe increases. Okay, those are the laws of thermodynamics, and they are used in various situations. I'll try to show you some situations in which they're used, but we're going to talk specifically about how you might build a device called a heat engine. And actually, any engine is a heat engine. Sometimes the word heat seems superfluous, but there you go. Heat engine is a device that takes some of the flow of heat and makes work out of it. So there's a conceptual diagram for a heat engine, and we're not going to talk about right now exactly how you would build one, but we will in just a moment. But every heat engine needs two things. First of all, we need a hot reservoir. Now, a hot reservoir is at high temperature, and it has, and the temperature will not change much if we get heat flow out of it. Okay, so yes, a burning match is hot. It's at high temperature, but there's not much match there. And if you start to take heat out of the match burns and it goes out very quickly. So that's not a very good hot reservoir. What would be a hot reservoir? Well, how about this? How about an entire pile of burning wood? Okay, now that's going to stay burning for a lot longer. And even if we take some heat away from the fire, which naturally happens when you burn a fire, the temperature of the fire stays hot. Your body could be considered a hot reservoir. I mean, it's a mildly high temperature compared to the environment, and as long as you are alive, your body temperature stays high. So a hot reservoir. The other thing you're going to need is you're going to need a cold reservoir. And as you can imagine, the cold reservoir is at a low temperature, at least low relative to the high temperature hot reservoir, and the temp doesn't change much. If heat enters. Some cold reservoirs that are used for heat engines, the atmosphere of the Earth is at relatively low temperature compared to fires, and you can dump heat into the atmosphere of the Earth. It's a very large amount of atmosphere, so its temperature doesn't rise very much. The ocean is an excellent cold reservoir because of the specific heat of water. So a lot of times we use the ocean as a cold reservoir. And if you have these two things and you put them in contact with each other, you're going to naturally get a flow of heat. Now that doesn't really help us out a lot. But what if we were to have some sort of device interposed in between these two? And we took our hot reservoir and our cold reservoir, and this device would take a large amount of heat out of the hot reservoir. Most of it would go into the cold reservoir, but some of it could be taken to the side So this is QH, the amount of heat that came out of the hot reservoir, and this is a smaller amount, QC, the heat that goes into the cold reservoir, and this is the work. This is a conceptual diagram for a heat engine. And I've got the hot and cold reservoir offset a little bit here because of my camera's in the way. But this is a conceptual diagram, and it is important that this be a wide swath here and that this be a narrower swath here and there, because conservation of energy says that the heat that leaves the hot reservoir is equal to the combination of the heat going to the cold reservoir plus the work that we stole. So if this is a 10-lane highway and this is 6 lanes, then that's going to be 4 lanes worth. That has to add up this way. Now, why can't we just take all of the heat and have it flow? Well, unfortunately, the third law of thermodynamics does not permit us to do this. Well, actually, the second law of thermodynamics does not permit us to do this, to take all the heat from the hot reservoir and turn it all into work. This is not allowed. It's not allowed because the heat will not flow from the hot reservoir unless it thinks it's going to be going to the cold reservoir. So there is a maximum amount of heat that we can steal here. And then if you try to steal more work away and the heat shrinks too much, the process stops. So there's a limit to how much work you can get out of a heat engine. There must always be some heat flowing to the cold reservoir. This is called the waste heat. Now, it's not wasted in the sense that, well, it didn't turn into work, so it's wasted in that sense, but it isn't somehow inferior. It absolutely must be there to make the process happen. But it's often called waste heat because it goes into a cold, low temperature thing. And once heat enters the low temperature body, it's hard to get it back out because heat flows from high temperature to low temperature. Okay, so this is not allowed over here. I'm going to go ahead and do this right here, okay? And then there is one more diagram I wanted to draw for you, and that is where you have your hot reservoir at the top and the cold reservoir at the bottom. And what if we were try to make heat flow up from cold to hot? Well, we could do that so long as we added some work. So heat flows from the cold reservoir, gets some work that we have to do some other way added to it, and then gets pumped into the hot reservoir. And this is a refrigerator. Oh, I put a D in there, didn't I? There we go. Clean up my mistakes. This is a conceptual diagram for a refrigerator, which is a heat engine running in reverse. And you'll have to put some work in. So this is what happens inside. This is the cold interior air of your icebox or refrigerator in your kitchen. This is the electricity flowing through the compressor that does some sort of magic stuff on some sort of fluid in there. And then the heat gets pumped into the air around the refrigerator into your kitchen. So that's why people who stuff a bunch of things next to the refrigerator, like I used to stuff the grocery bags next to the refrigerator, and my refrigerator's in a little alcove to begin with, and my refrigerator stopped working so well because it was unable to have this heat dumped into the kitchen. So I had to take all those plastic bags away from the side of the refrigerator, make sure the refrigerator had about a few inches of airspace all the way around it. Then my refrigerator worked much better. It wasn't costing me $1 million in electricity. So this is a refrigerator. This cannot happen, and this is a conceptual diagram of a heat engine. We'll be talking about this in a minute. What I'd like to do is make another video real quick here and show you practically how some real heat engines work, how you would affect this kind of a thing right here.